Do you know the difference between an octopus and a group of computers? Well, I'm going to give you the answer. It's time. Yes, time. Sounds like a joke, but it's actually a very serious 25-year-old problem called the 8 fallacies of distributed computing. And that's going to be the topic of my talk. I am Sébastien Bigot, I'm with Bell Labs in France, and this starts with a vision. A vision of the future. It's not difficult to anticipate that traffic in the future is not going to be dominated by me talking to my neighbor, me talking to a machine, but machines talking to machines. The interest we are thinking of machines and using machines is that they are much more powerful than humans. They can also very easily and massively collaborate. They are versatile and always available. And last but not least, also capable of mission-critical tasks. So it's quite interesting to think of the future as optimal if we were able to design IT networks if they were engineered for interacting machines. This is the outline of my talk. I show you, yes, that in the beginning there's time. And the reason why we worry about time now is because the landscape of IT and telecom is changing. Then I come to that 25-year-old problem called the 8 fallacies of distributed computing. I show that, yes, it's time to shake these fallacies. We have the technology to do that now. And then I will conclude. If you think about massive cooperation of robots, the first place that could come to your mind is a data center, where you have thousands, sometimes millions of robots cooperating. But still, there has been different strategies to make them cooperate. Do you prefer to use the flexibility of multiple CPUs? Or is it better to use massively parallel GPUs working together? Similarly, do you prefer to use massively interconnected CPU-based servers, or do you prefer mainframes? If you think about those two examples, the underlying difference comes with their way time is organized into these machines. Here's time. And the connection with optics is obvious. For as long as this industry has been worrying about transporting data with light, the focus has been on time to transport. That means optimizing bandwidth and distance, the bandwidth and distance challenge. But when you wait, when you send a message, there are all the reasons why you can wait. And you can also wait because it takes time for you to dial, to reconfigure. That's what I'm calling the turn up, tear down challenge. And last but not least, generally we are a large number of people converging, or machines converging into the same hardware. That means if we are all together, we need to wait. That's what I'm calling the time to queue, the latency and jitter challenge. In the past, obviously the focus was only on time to transport because it was by far the largest and the dominant source of waiting time of all. Now, there are places in the network where the other two dimensions of time matter almost as much. And that has to do with the edge of the network, close to the machines or to the users. And the reason why I'm saying that is because the landscape is already changing. Changing in what sense? This is a picture of the typical time it takes to establish a transport service in an optical network, as opposed to the typical time it takes to establish an IT service inside a data center. As a function of time, we've seen a radical evolution. It used to take days, even months, to do manual reconfiguration of networks in the year 2008, for example. Everything was manual, and still largely is. Where in the data center, you would also have a lot of manual operation when you would turn a hardware server up. As time was going on, then we started to remotely configure networks. And in data centers, virtual machines started to appear. And of course, that saved a lot of time in order to reconfigure them. Then the autonomous mode of reconfiguration of optical networks starting to be a reality, role-based type. That was like, it's about now. And in data centers, the reason why data centers are more powerful today is essentially because they are using microservices on top of virtual machines. So what could the future look like? Maybe cognitive, artificial intelligence-based optical networking to be compared with high-performance distributed computing. But what I'd like to point out is the trend. Those two typical times actually converge to become very similar. It's the first time in history that optics and electronics can do almost the same thing with the same reactivity. What opportunity does that open? 5G comes with new expectations and opportunities. Yes, a lot of people are asking for time to be controlled. That's a representation of the typical services where you see the latency as a function of bandwidth. You see the virtual reality, virtual RAN, the vehicles that are very demanding in terms of latency, as well as sometimes bandwidth, and other applications which I will not be worrying too much today. Still, if you focus on those very demanding applications, you can even segment them further into those who require typically 10 millisecond reactivity. I'm calling them real time. If you want vehicles, autonomous control, well, you can call them time sensitive. And in factory floors, they typically demand even more. And that's the same for vRAN. They would go for less than 100 microsecond typically latency requirements. So there are actually different levels of requirements in terms of time and bandwidth for different services. The way we can, the type of key performance indicator to compare those services would be in terms of latency, jitter, packet loss, dynamics. And is that possible to play with just the regular video, the best effort traffic? All those kind of things can become a reality. But again, it is becoming a reality because 5G is coming. And because no one can beat the speed of light, there's a massive trend that is popping up, which is radically changing also the landscape in that field. The reason why we can worry about time now is because of the time it takes now to carry data in the new cloud environment that is coming. In today's cloud, the distance to the nearest central DC can be in the range of thousands of kilometers. That means machine-to-machine communications are essentially located inside data center, and they stay inside. And then once you go out of the data center, you get to another data center or to the user. So there's some form of silo that breaks what happens inside data centers and what's happened between data centers. Tomorrow, and that's happening today, the distance to the nearest data center is going to be much smaller, in the range of a few tens of kilometers. That's what we call an edge data center. You will have many of them. And then the novelty is that machines-to-machine traffic will naturally flow across those small data centers, across the metro edge cloud, DCs. That means we have a new infrastructure coming, a new infrastructure where we'll have distributed IT resources. You can leave them where they are just to be used to control the network, or leverage the fact that they truly offer new opportunities in the way to master time, if we connect them adequately. And that's where nature comes in the game. We, because probably it's a bias we have, tend to believe that as humans we are the most advanced creature on Earth. We have a nervous system that controls our decision. And it's actually 2 layers of decision. The most complex ones are made inside the central brain, central system, whereas the time-sensitive reflex reactions, in case you get burned or anything that makes your life threatening, that is a threat to your life, is going to be driven by your spine, and that's a very distributed nervous system. So is that truly the most advanced cognitive system on Earth? Well, it happens that Mother Nature invented something else, which is even older than we are, and that is the octopus. They have a very flat cognitive nervous system. Yes, it is already distributed. It has 8 local brains inside the tentacles, orchestrated by a central brain. And they cooperate very efficiently. That's truly a multi-domain cooperation and synchronization between the local brains. And that allows for distributed time-sensitive reactions and also distributed complex decisions. And it's very much like that disaggregated network, because you can perform, or the tentacles perform almost autonomously after cut. And they can also be restored after they are cut. So it's kind of a pay-as-you-grow system. And by the way, some say they were very close to dominating the world. So, yes, there's another mode of managing time, and a better way that could be inspired by those octopus networks. It happens when you think of that story, that it's about interconnecting PCs, computers, in a very massive fashion. So, what if we could make something similar to the octopus nervous system? So, when you think about machines, cooperating machines, then if you look over internet, something pops up very easily that the scientists, experts in computer science know very well. And that problem was phrased 25 years ago by a guy named Peter Deutsch, who found a list of fallacies that young programmers generally do when they do their applications. They essentially overestimate what the network can do. And these fallacies are listed on the right. It's very easy to find over Wikipedia. Just type distributed computing, they will pop up. And what those fallacies say are: the network is reliable, latency is 0, bandwidth is infinite, the network is secure, topology doesn't change, there is one administrator, transport cost is 0, the network is homogeneous. Don't worry, I said them really fast, but I'll come back to each of them in detail in the rest of the presentation. But do we have to live with these fallacies? How far are we from turning these fallacies into realities? Well, again, it largely boils down to time. If you look at, this is a measurement conducted in my lab, where you see, as a function of the number of flows competing to one output port of a switch, you see the average latency. At low load, yes, you would expect a low average latency, and as load increases, you would expect the latency to grow as well. But what matters much more than the load is the number of simultaneous flows that want all together to go out. It's not so much the total load, it's how many of those flows are competing to go out. So what that graph shows is that standard packet-based switching fails because of latency fluctuations. And we call that jitter. Yes, there's a new form of edge networking that can move away from that model. It started with what I said, standard switching fail. And you cannot control time, jitter comes in the game, but you can't use circuit switching. Circuit switching is very nice to control time, but it's not economically viable because it's too rigid and costly for a data center-like traffic. So the dream to solve the 8 fallacies of distributed computing would be to have a single conversion platform that can at the same time host the most time-sensitive apps, where lower and higher time bounds should match. We call that deterministic networking, and at the same time be very reactive to the video type of flow, like the dominant best effort traffic that go across edge data centers. The combination of the two is what we call dynamic deterministic networks. What is a dynamic deterministic network? Think about your worst waiting experience. This is about time, right? Where are you? I'm sure you recognize that picture. This is an amusement park. And how did these guys solve the problem of waiting? Well, Disney created the Fast Pass. And the subtitle of this is "Get a time, why wait in line?" The trick is to eliminate latency fluctuations by reserving. You reserve a time slot. In Disney, it's half an hour. In our test bed, it's going to be 1 microsecond, 10 microseconds, depending on the bed choice. But it's a fixed duration time slot. And we use that as a data container. So it's actually what we call a slot. And all data container come after each other. So they are synchronous. And what we would like to do is reserve slots. Not for all traffic, not for the average video, but just for the time-sensitive traffic. Say it's about 10% of the overall traffic. And the rest is going to be opportunistically allocated for best effort traffic. Exactly in the same way that if you go to Disney and you're not a VIP, you didn't pay for the Fast Pass. You just queue and you wait until you have a slot. So that technology, we call it 3S. And we believe 3S networking can change a user's wasting experience in the same way Disney did it with Fast Pass. How does it go? How does it fulfill or change the fallacies? We did that experiment where we combined two such 3S technologies into two domains. We actually interconnected an edge cloud, with a technology we call cloud burst optical slot switching for intra-data center communications. And we interconnected it with a backbone technology called optical Ethernet, which is also 3S and is meant to carry data in the same deterministic fashion. So we combined the two, and this is what we got. That, by the way, not only applies to communication network of today, but also to the communication of the Industry 4.0 enterprises. Yes, we need to make that at the application level. What makes you wait is whether your application goes through. It's not just a big pipe of data that needs to go across. You need to worry about end-to-end deterministic performance. So in those two technologies, we made sure that when we go from one technology to the next, there's a buffer which is fully aware that the traffic that goes through, when it is deterministic, needs to be managed in a different way. And that's what we managed to do, such that, yes, the end-to-end deterministic performance is preserved. That was a paper that we presented at ECOC in 2018. How does it work? You see here the result, the measurement we obtained. These are results out of millions of flows that were measured, and we measured the time for each of them to arrive. And you see the difference between DDX technology, where you have a very clear latency in the range of 60 microseconds, to be compared with, yes, a good average, sometimes even better than DDN, less than 20 microseconds, but a very long tail that go up to almost 200 microseconds. So yes, DDN is truly about providing a perfect timing, all equal for all the flows. Why do we need to do that? Again, this is a cooperation of machines. Cooperation of machines, if you think about another environment where you need to cooperate, would be a meeting. If you want an efficient meeting, yes, you don't want the participant to be late, but you don't want them to come earlier either. An efficient meeting is when everybody comes on time. Not early, not late. That's determinism. Can we really break Deutsch's fallacies? 25 years ago, Peter Birch said the network is reliable, and he said that's a fallacy. Well, in legacy network, typically the data loss ratio is 10 to the minus 3. With DDN, the example we're showing you, we can do much better than 10 to the minus 9 data loss ratio. So we have more than 1 million in terms of gain. 25 years ago, Peter Birch said latency is 0. Well, with legacy switching, typically you have 100 millisecond latency and 10 microsecond jitter. With our testbed, we measured 100 microsecond latency and just 10 nanosecond jitter. That excludes end-to-end propagation, of course, but still it's 1,000 gain. In terms of bandwidth, the third fallacy says bandwidth is infinite. Well, yes, with legacy, you still can go relatively high at 100 gigabit per second. In our testbed, because it's optic and coherent optics, it can go higher than 1 terabit easily. That's all, at least a factor of 10 of gain. Fallacy number 4. 25 years ago, Peter Birch said the network is secure. Oh yes, it's a challenge today. And for that, we use typically VLAN, which is a form of software slicing. With DDN, you can do much better. You actually organize hard slicing per flow. Dedicated hardware for each of your flows, so it's end-to-end secure by design. Fallacy number 4, topology doesn't change. Well, yes, true. If you change the network, you will have discontinuities in service upon changes. With DDN, the way it's set, you can do hot and heatless reconfiguration upon changes. I don't have the figure yet of how much that fast is, but I can point to one of the papers that my colleague Michael Sversban provided at ECOC this year. Fallacies number 6, there's only one administrator. Yes, in legacy there is a per technology domain control. With DDN, well, it's designed to have an end-to-end orchestration of everything. So someone owns and runs it all. It's for verticalized businesses. Fallacies number 7, transport cost is 0. Yes, in legacy, transport and switching costs add up. Well, with DDN, obviously transport and switching out are 1. Because that 3S technology is exactly what it does. Combine transport and switching at once. Fallacies number 8, network is homogeneous. Well, true. Circuit and packet technology side by side with specific control. That's the reality of today's network. With DDN, yes, it's a change. You need to modify some hardware, but slotted synchronous scheduled networking is over all the edge network. I'm not saying it's going to go up to the core network, but still you have an homogeneous network where it matters the most, where timing matters the most. So as a conclusion, if you want to solve for the next generation of 5G in the edge cloud, it's like solving for the 25-year-old dream of distributed computing. And if you narrow down the problem to the strict control of time, to edge network, and to time-critical flows, under a common denominator technology based on TDM, slotted, synchronized, and scheduled, 3S, then the 8 fallacies of distributed computing are whole it, and that paves the way for the Octopus infrastructure. Thank you for your attention.